Day 17, we're going to be looking at radicals and conjugates. You guys know what radicals are. Probably aren't used to hearing that term, but we're talking about square roots, cubed roots of numbers. Alright, so I want to start off just really quickly up here in the corner where I've got some blank space. And I want to talk about the square root of a product. Alright, so if I say the square root of 4 times 9, then I could actually look at that a couple of different ways. I can go ahead and multiply that as the square root of 36, which means what? Square root means what times itself would give me 36, so that would give me 6. Or I can break it down like this. I can take the square root of 4, which is 2 times 2, and the square root of 9, which is 3 times 3, and then I can get to the square root of 36, which is the square root of 6 times 6, which equals 6. Okay? So the multiplication of radicals, or square roots, can be worked like this. Let's think about division for just a second. What if I have the square root of 25 over 16? I can work it the exact same way. I can work it as the square root of 25, which is 5 times 5, the square root of 16, which is 4 times 4. So the square root of 25 over 16 is 5/4. Okay? So that holds true with square roots, that holds true with cubed roots. But what about addition, subtraction of radicals? Let's look at this. Let's look at our opening exercise. Which of these statements are true for all A if B is greater than 0? And explain your conjecture. Explain why you're saying it is. Alright, so if I look at the first, second, and third ones, I want you to pause the video and I want you to see if you can figure out which ones are true. Which ones are always going to be true if B is greater than 0. Hopefully you figured out that statement number 1 and statement number 2 are true for all A and B. Statement number 1 is true because all I'm doing is using the distributive property. 2 times A plus B is the same thing as saying 2 times A plus 2 times B. So that one is true, no matter what I put in there. Statement number 2, A plus B divided by 2 is the same thing as saying A divided by 2 and B divided by 2. I can put any number in there and it's going to be true. But let's look at the third one. The square root of A plus B is equal to the square root of A plus the square root of B. Will this ever be true? It's actually going to always be false. Alright, and we're going to show that. But let me give you an example for just a second. Let's say that I want to do the square root of 9 plus 16. Alright, so that would say the square root of 9 plus the square root of 16. And I'm going to put that question mark above there because I don't know if it's true yet or not. Alright? So, square root of 9 plus 16 is the square root of 25. The square root of 9 is 3. The square root of 16 is 4. does not. So therefore, this statement is false. All right, this statement is false. All right, so that is always going to be false. So this statement here is always going to be false. All right, example number 1. An expression is in simplest radical form when the radicand or the expression under the radical sign, guys, this is a radical sign. You need to know that. We talk about square root. That is called a radical sign. So an expression is in simplest radical form when the radicand or the expression under the radical sign has no factor that can be raised to a power greater than or equal to the index, either 2 or 3. And there is no radical in the denominator. All right, so let's talk about this. Let's do an example. Express the square root of 50 minus the square root of 18 plus the square root of 8 in simplest radical form and combine like terms. All right, so first of all, we're going to do each part separately. And then we'll come back and do it all together. So I'm going to look at the square root of 50, the square root of 18, and the square root of 8. Now guys, remember when we do square root, we're looking for something times something that will give, something times itself, that will give us a perfect square. 50 is not a perfect square, 18 is not a perfect square, and 8 is not a perfect square. But, let's look at this. Can I break 50 up into something times something, and one of those numbers be a perfect square? I can. I can break it up into 25 times 2. Now remember, I can break this up now as the square root of 25 times the square root of 2. And that gives me the square root of 25 is 5. And then the square root of 2 cannot be broken down anymore. So this is what I end up with, 5 square root of 2. Let's look at 18. It's not a perfect square, but there is something I can rewrite that is a perfect square. 9 times 2. So that's broken down into the square root of 9 times the square root of 2. The square root of 9 is 3, because 3 times 3 is 9. And the square root of 2 cannot be broken down anymore, so therefore I have 3 square root of 2. Let's look at 8. Not a perfect square, but I can break it down. I can break it down into the square root of 4 times 2, which gives me the square root of 4 times the square root of 2. Square root of 4 is 2. 2 times 2 is 4. So I end up with 2 square root of 2. So now, here's what I can do. I can take and rewrite this. So the square root of 50 was 5 square root of 2 minus the square root of 18 was 3 square root of 2 plus the square root of 8 was 2 square root of 2. All right, now it says combine like terms. So how do we know they're like terms? Guys, here's how I know these are like terms. They all are attached to a square root of 2. It's kind of like an x. If they all have an x, I can add them together or subtract them from each other. Same here. So I can combine 5 minus 3 is 2, plus 2 is 4, and then the square root of 2 stays the same. All right, so my answer here would be 4 square root of 2. Okay? Let's look at our exercises. Do not flip out. Do not flip out. You're all looking at number 1 going, oh my gosh, it has a fraction. It's hard. Do not flip out. All right, so the square root of 1/4 plus the square root of 9/4 minus the square root of 45. All right, so we need to look at this and do the square root of 1/4, the square root of 9/4, and the square root of 45. All right, let's do the square root of 45. We'll start with the easy number. Square root of 45, 45 is not a perfect square. I have 36, 49, but 45 is not. So now let's see, can I break it down into anything times anything, but one of those numbers be a perfect square? I can break that down into 9 times 5. All right, so the square root of 9 is 3, square root of 5. Okay? Let's look at 1/4. How do I know if 1/4 is a perfect square? Well, you can do it a couple of different ways. I was looking at my calculator here. The only bad thing here is with the calculator, if you wanted to actually try this on the calculator, the only bad thing about it is I can do 1 divided by 4 and then square root that, and you're going to see that 1/2 is the square root of 1/4. 1/4 is actually a perfect square because 1/2 times 1/2 gives you 1/4. 9/4, guys, look at 9 and look at 4. They're both perfect squares. The square root of 9 is 3. The square root of 4 is 2. So the square root of 9/4 is 3/2. All right? Now let's combine those, or let's rewrite them. So 1/2 plus 3/2 minus 3 square root of 5. 1/2 plus 3/2 is 4/2 minus 3 square root of 5. 4 divided by 2 is 2 minus 3 square root of 5. Okay? All right, look at number 2. Number 2 says, let's do the square root of 2 times the square root of 3 minus the square root of 2. Guys, look at this. This does not require the square root of 2, the square root of 3. They are the smallest that you can get. You cannot break those down anymore because they're both prime numbers. We can't do anything except perform the operation. Guys, distributive property. Square root of 2 times the square root of 3 is the square root of 6. Okay? Square root of 2 times the square root of 2. When I multiply the same square roots together, that gives me the square root of 4, which is 2. So in this case, square root of 6 minus 2. I'm done. There's nothing else I can do. I am in simplest form because the square root of 6 cannot be broken down into any perfect square times something. 1 is not a perfect, or 1, 6 is not a perfect square, 2 is not a perfect square, 3 is not a perfect square. Those are the only 4 factors of 6. So I can move on, I'm done. Alright, square root of 3/8. I can break that up, and I can look at it as the square root of 3 over the square root of 8. Alright, square root of 3 is as far as it can go. Square root of 8. Let's see. I'm trying to think of the easiest way that we can do this so that we can get rid of, I really want the radical to not be in the denominator. Alright? Remember I told you a little bit ago, the definition, simplest radical form when the radicand has no factor that can be raised to the greater power or equal to the index, and there is no radical in the denominator. So I've got to do something here. I've got to figure out how to get rid of this radical in the denominator. So let's think about this for a second. Square root of 8, that is not a perfect square, but is there anything I can do to that to get it to be a perfect square? Well, let's think about the multiples of 8. 8, 16, 24, 32. 16 is a perfect square. So what if I multiply everything times the square root of 2? What if I do that? I multiply everything times the square root of 2. I end up with the square root of 6 over the square root of 16. And notice I multiplied by the square root of 2, because if not, I'm just multiplying by 2. That would give me 2 square root of 3, 2 square root of 8. So I'm multiplying everything times the square root of 2 to get rid of that radical. Square root of 6 we've already determined you can't do anything with. 16, the square root of 16 is 4. So I'm finished. I have gotten it in simplest form. There's no radical in the bottom, so we are done. Alright, cubed root. Guys, this is no longer square root. We are looking at cubed root here. That little 3 tells me it is the cubed root of 5/32. Alright, so you can grab your calculator and you can say, okay, 32, and I'm going to cube that. Look what it gives me. So it is not a perfect cube. Okay? So I've got to figure something out. I got to figure out something that I can do to multiply here. What if let's see, perfect cube. 32, 64, 64 is a perfect cube. So I'm going to multiply, let me rewrite this. I'm going to multiply by the square root of 2. So that now gives me the cubed root of 10 over the cubed root of 64. Alright. When I use my calculator, if you need to, I find out that the cubed root of 64 is 4. And the cubed root of 10, I can't simplify that in any way, because nothing times 10 or nothing times anything will give me a cubed root. 1's not going to work. 2 won't work. It's not cubed. 5 is not a perfect cube. 10 is not a perfect cube. So we're as simple as we can be here. All right, so now we've got the cubed root of this 16x to the 5th. All right, so let's think about this. I want to break it up. I'm looking at something times something, and one of those needs to be a perfect cube. So 8 is a perfect cube. So 8, and I'm going to show you something here in just a second, times 2. Now let's deal with that x. What would give me x to the 5th? Well, I can do x cubed and x squared. And now I've broken this up into a perfect cube all the way around. So the cubed root of 8 is 2. The cubed root of x cubed is x. All right. And then, is there anything I can do here? No, 2 is as small as it's going to go. And so now I've got 2x cubed root of 2x squared. And I'm finished. All right, so we use, in the examples and the exercises that we just did, we use 4 properties of radicals. All right, so let me write those properties of radicals. We use the property of the square root of a times the square root of b gives me the square root of ab. All right, that's the first property we used. We use the square root of a divided by the square root of b is equal to the square root of a over b. That's the second property that you saw. Third property that we saw dealt with cubed roots of a times the cubed root of b gives me the cubed root of ab. And the fourth property that we saw was the cubed root of a divided by the cubed root of b gives me the cubed root of a over b. Okay? When do these identities make sense? All right? These were things that we used. When did they make sense? They made sense for square roots when a was greater than or equal to 0 and b was greater than or equal to 0. And when b was not 0, when b was in the denominator. They made sense for all cubed roots when b was not equal to 0, when b was in the denominator. All right, so just make sure you understand that there's certain times that b cannot be 0. All right, so let's look at example number 2. Multiply and combine like terms, then explain what you notice about the 2 different results. All right. The first product, let's look at the first thing. All right, so we're going to do the square root of 3 plus the square root of 2 times the square root of 3 plus the square root of 2. Okay? So let's look at what we're going to do. Distributive property here. We get square root of 3 times the square root of 3 plus, and I'm going to put these in parentheses, that way it kind of helps me keep them together, plus the square root of 3 times the square root of 2 plus the square root of 2 times the square root of 3 plus the square root of 2 times the square root of 2. Okay? Let's look at this. Square 3 times the square root of 3 is the square root of 9. Plus square root of 3 times the square root of 2 is the square root of 6. Plus square root of 2 times the square root of 3 is the square root of 6. Plus square root of 2 times the square root of 2 is the square root of 4. Let's see what we can combine. Square root of 9 is 3. Plus, I have the square root of 6 plus the square root of 6. How many do I have? I have 2 of them. Sorry. And then the square root of 2, or square root of 4 is 2. Alright. So 3 plus 2 is 5, plus 2, square root of 6. I'm finished. Guys, this is a radical expression. I know it's a radical expression because it has a radical in the answer. Let's look at the second part. Alright, so it wants us to do the square root of 3 plus the square root of 2 times the square root of 3 minus the square root of 2. Alright, and maybe you can predict what's going to happen here, but let's look at this. So square root of 3 times the square root of 3 minus square root of 3 times the square root of 2 plus square root of 2 times the square root of 3 or minus square root of 2 times the square root of 2. Okay? So square root of 3 times the square root of 3 is square root of 9 minus the square root of 6 plus the square root of 6 minus the square root of 4. 3 minus the square root of 6 plus the square root of 6 minus 2. Combine what I can. 3 minus 2 is 1. And negative square root of 6 and positive square root of 6 cancel out. So look at what I have. I have 1. This is not a radical expression. This is an integer. What do you notice about the two problems? The first product is a radical expression. The second's an integer. The second product has the nice feature that the radicals have been eliminated. In that case, we give the two factors a special name. Two binomials of the form square root of a plus the square root of b and the square root of a minus the square root of b are conjugate radicals. Alright? So if I have square root of a plus the square root of b times the square root of a minus the square root of b, these are what we call conjugate radicals. Okay? These are what we call conjugate radicals. For an expression in two terms, at least one of these contains a radical. Its conjugate is an expression consisting of the same two terms but with the opposite sign separating the terms. So in other words, they look identical, but one's positive, one's negative. Okay? So for example, the conjugate of 2 minus the square root of 3 would be 2 plus the square root of 3. Okay? Alright, so I've introduced you to now conjugate radicals. Find the product of the conjugate radicals. Alright, so this should not be difficult. They are conjugate radicals, guys. Go back and look at our conjugate radical. What happened to our middle part? It canceled out. So the only thing I had to figure out was the first part and the second part, or the last part. So square root of 5 times the square root of 5 gives me the square root of 25 minus the square root of 3 times the square root of 3 is the square root of 9. So this would be 5 minus 3 would give me 2. I don't have to worry about multiplying the middle because it cancels out. With them being conjugate radicals, it cancels out. 7 times 7 is 49. They're conjugate radicals. Minus the square root of 2 times the square root of 2 is the square root of 4. Excuse me. So 49 minus 2 is 47. That's all I have to do. Done. It's really nice dealing with conjugate radicals. They're conjugate radicals, guys. Same numbers. The only thing different is the signs. So I have square root of 5 times the square root of 5, which is the square root of 25. Minus 2 times 2 is 4. So 5 minus 4 is 1. All I'm doing is doing the first step to distributive property and the last step to distributive property. I am forgetting all the middle. Alright, I'm forgetting all the middle stuff because the middle stuff cancels out. Alright. Look at example number 3. So now we're going to see how division by a radical can be reduced to division by an integer by multiplication. Alright, so it says write the square root of 3 divided by 5 minus 2 the square root of 3 in simplest radical form. Alright, so here's what I can do. And this is why they introduced you to what they call conjugate radicals. Guys, if you take this back here, we were trying to figure out what we could do to get a perfect square on the bottom. This one was nice because all I had to do was multiply by the square root of 2 to get the square root of 16. This one's not so pretty because it's not just one number. It is 5 minus 2 square root of 3. So I can use conjugate radicals. Alright, so let me show you how I can use conjugate radicals. So here's my original problem. I can multiply by the conjugate radical. But when I multiply the bottom, I have to multiply the top. So I'm going to multiply conjugate radical means it's all the same except for the sign. So I'm going to multiply everything times 5 plus 2 square root of 3. Let's see what happens here. I'm going to start at the bottom because we already know how to do the bottom part. 5 times 5 is 25. And then 2 square root of 3 times 2 square root of 3. I'm going to come over here for just a second. And I want you to see what happens here. I'm going to multiply everything outside the radical. So 2 times 2 is 4. Square root of 3 times square root of 3 is square root of 9. Square root of 9 is 3. So this becomes 4 times 3, which is 12. So now all I've got here is 25 minus 12. My radical is now gone from the bottom of my problem. Alright, so I've got to multiply 5 times the square root of 3 and then add 2 square root of 3 times the square root of 3. Alright, so 5 times the square root of 3 is 5 square root of 3. 2 times the square root of 3 times the square root of 3. Alright, so let's come over here. I'm going to show you this one again. 2 times 1 is 2. Square root of 3 times square root of 3 is square root of 9. Square root of 9 is 3, so 2 times 3 gives me 6. 25 minus 12 is 13. Let's look at this. Square root of 3 is as small as I can get. There's no radical in the bottom, so I'm finished. The process for simplifying an expression with a radical in the denominator has 2 steps. Alright? Alright, so this is the process for simplifying an expression with a radical in the denominator. Okay? It's 2 steps. You're going to multiply the numerator and the denominator. Alright? Of the fraction by the conjugate of the denominator. Alright, make sure you're multiplying it by the conjugate of the denominator, which is what we did up here. We took the conjugate of the denominator and multiplied it. And then simplify the resulting expression. Okay? Guys, that's 2 steps. That's it. All right? If you have questions, make sure you reach out.